Welcome everybody back from the coffee break, and thanks for the speakers for the next session to be here. Welcome. So we're really happy to have you here, bringing the insights of the private sector into the fusion field. So this morning we already had an overview from Ambrogio Fasoli from Eurofusion, and then a virtual tour of ITER by Kirsten. So now we are looking forward to seeing the perspective of the private sector into fusion. So I guess I will not take much more time out of this, just to explain a little bit how the session is going to be for the attendees. So we're going to have a quick pitch from each of the speakers here about the work done in their own companies. So just a short 5-minute presentation, and then we're gonna move to a panel discussion where we're gonna tackle some questions interesting for the audience, but also at the same time we will be taking questions from you, as we have done it before, in the chat. So in the panel discussion we will deal with some questions, but also we're looking forward to receiving your questions and answering them live during the event. So I guess without further ado, I will give the word to Daan van Vugt. So he's the representative, and as far as I understand, the founder of Ignition Computing. So please, Daan, go ahead.
Thank you, Dario. Yep, that's right. I've done a PhD in fusion and then founded, let's say, a support organization for computing and fusion. I'll give a brief introduction, and then I guess we go on, and then we have questions afterwards. So let me share this this deck here. All right, can you see these slides?
Yes, we can.
Yeah, so we are a consulting firm. We develop software for science and high tech, specifically focusing on nuclear fusion. We do a lot of work for ITER, for instance. We are based in Eindhoven, in the Netherlands, since almost 5 years. We have two major fusion clients, ITER and Pacific Fusion, who are doing well, Z-Bench-like approach, building pulsars for that. We work mostly on improving numerical methods, improving simulation codes, helping with machine learning, high performance computing, visualization. And we have a variety of clients and partners in, well, mostly the Netherlands and France. I'll give some examples of projects that we've worked on, but there are several more, and this can come up with questions later, I guess. The most important thing that we do with IMAS software is kind of supporting this standardized data model that ITER has developed, and is meant to facilitate coupling multiple Gauss together, because in fusion there are a lot of different physics playing a role, and regardless of whether you're doing a tokamak accelerator or another approach, you have core plasma physics, ice plasma physics, you have neutronics, you have radiation, you have chemistry, you have a lot of different expertises, which means that there are many different codes around the world. And if you want to have let's say, a consistent answer, you need to have all of these codes simulate together, and this means that they need to have shared data structures or shared data format that they can go in. And so this is called the data dictionary, which is a massive set of standards and conventions on how to define your vector orientations, how to define your variables. And this comes with tooling to access from Python, C++, Fortran, Java, MATLAB, and to store this into a variety of locations, and to map this data onto the experimental results coming from the existing machines. We've also developed serialization and deserialization to efficiently couple codes together that may run in different places or on different languages. And this is something that ITER is planning to open source, so it's maybe interesting to look into if you are entering this field. And with this IMS data standard and the serialization tools, we are developing for ITER now a kind of basic flight simulator tool, the Pulse Design Simulator is called, where we combine a set of relatively simple and fast physics simulators with eventually the actual control system of ITER, or the actual software, but for now just a smaller surrogate. These different physics codes that run together perform different tasks, like simulating equilibrium, simulating transport, doing edge transport simulations. And these are all independent, running from different labs, or can be swapped out. With this tool, ITER will design their pulse schedules, so kind of plan what experiments they want to do and use it to inform the control targets that they can set, check that they don't go over limits, etc. Can also be used to optimize your controllers. And one more thing that we are preparing for now is to do data acquisition during the simulation, so that we can set up data sets to replace slower components with ML surrogates. Because the idea is that this flight simulator will be much faster than real time, let's say 5 times, 10 times as fast or so, because these ITER pulses are quite long. Otherwise, it will take really a long time to optimize your plan for a pulse. We also work in, let's say, inertial confinement fusion, as I mentioned before, and this is with the Flash code. We're working together with Pacific Fusion, who are based in San Francisco, near San Francisco. This Flash code is more or less open source, and we've made several significant improvements regarding actually being able to run their simulations at all. There were bugs in adaptive meshing, in their finite volume methods, problems with the divergence cleaning methods that they are using, stability of solvers, using maybe even more robust direct solvers. And we've stacked several 20 to 40% prompt optimizations. And this is a bit on these numbers are a bit on the conservative side. Depending on the case, it can actually be much more like that. Some cases have been 5 times as fast or so. So this is a significant impact for inertial confinement fusion. And we have our own R&D project on simulation speed up by ML without taking the risk of predicting outside of your data set, let's say, by combining ML solvers with iterative matrix solvers. So predicting the optimal solver and the parameters, generating preconditioners, and optimizing the reuse of them, which is a relatively advanced technique for that many simulation codes don't do yet. We're using ML to generate initial guesses instead of just predicting the solution. And the nice thing here is that we can guarantee the accuracy of the solution. Even if your ML model is mispredicting, we can patch this up with an iterative solver, typically. All of these projects have lead to quite a few internship opportunities, which I think also is something that people here may be interested in. So we have several available. I can share this list also later, and we're always open to discuss defining projects for people with interesting ideas. So we have several on this preconditioning, on this ML solver optimization. We have some on high order coupling between different components in simulations. And we will work, we have internships on this Pulse Design Simulator, which I just described. We are a FusionNet member, and so there is travel support and internship support available. And if you have any interest in that, you can contact us at this email below, which you'll find also on the website.
Oh, thank you very much, Dan, for the presentation.
Thank you.
We'll move right away to Anouk Nicolopoulos-Salle. I hope I pronounced your name correctly, Anouk. So great. So you're representing Renaissance Fusion. So please go ahead.
Yes. Can I share? Okay. Can you see my screen?
Yes.
So I am Anouk Nicolopoulos-Salle. So I'm an applied mathematician working as accelerator computer scientist at Renaissance Fusion. And to give you some context, Renaissance Fusion is a 60-person startup founded in 2020 in Grenoble in the French Alps with ultimate goal, the realization of fusion energy. So up. So the two big families of magnetically confined devices are tokamaks and stellarators. The big difference is that tokamaks are essentially easy to build and difficult to operate, whereas stellarators are difficult to build but easy to operate. And so this is where Renaissance Fusion comes into play, because we believe that the easiest way to reach the industrial fusion is to follow the deuterium-tritium stellarator device. There are three big challenges for these devices, which are the radioactivity, the very large size of the device, and the manufacturing of the coils, which are very twisted. And we propose three innovations to tackle each of these challenges: liquid metal walls to absorb the radioactivity, high temperature superconductors that can induce very high magnetic fields and therefore release the constraint on the size of the machine in the triple product formula that is in the slide, and simple shaped coils, laser engraved to produce 2D complex current patterns on the wide HTS that we will build. So now let me introduce each of these pillars a bit more in details. So our stellarator, which is called Chartreuse, like the mountain range that we see from our office, is aiming to produce a 10 Tesla magnetic field on axis. So this means that it's a magnetic field twice as strong as the planned power plant of the family of Wendelstein 7X that you see on the left, but that is still the same size as Wendelstein 7X. So this compact configuration is actually made possible thanks to these HTS magnets. And this program is of major importance for us because we are becoming leading producers of HTS, which are in high demand. And actually, any application with a target magnetic field can be approached with these HTS. It boils down to an inverse problem to find the laser pattern to recreate this magnetic field. So now the second pillar is actually very related to the wide HTS magnets. It's about revolutionizing the stellarator's coils, because the traditional way of manufacturing these coils is to start from HTS tapes of a few millimeters, to bundle these tapes into cables, to wound these cables into a coil, and finally to place them with millimetric precision. And so thanks to the wide deposited HTS foils, we can skip the cable step and also the winding around the complex non-planar shape. And we are left with laser patterning process that will enable us to produce complex 2D currents instead of 1D currents along the complex coils to recreate the magnetic field. And so we developed a benchmark program and have been able to reproduce the fields of a gyrotron and of an MRI. We submitted an article with the details. You can find it on the archive. And the next step, which will be a big breakthrough, is a reproduction of the Wendelstein 7X magnetic field configuration. So now about liquid metal walls. Liquid metal walls will flow inside the vacuum chamber, making the reactor safer because they will catch the neutrons, which will react with the lithium to release tritium and produce fuel. And it will flow at 1 meter per second, more or less, extracting heat from the device. And we will actually use the magnetic field inside the device to control it and to make it stick to the chamber. So there is a video of an experiment that we did in our lab online. So I put the link here. I will send the slides to Dario. And so it's really important that we all work together as a team of experimentalists, theoretical and numerical scientists to prove that this technology is part of the solution, right? And so to finish, I'd like to remember that what makes us special is that we will make our own HTS, that thanks to these wide tapes we are building, our stellarators will be easily manufacturable. And last takeaway message is that you can definitely be a part of it because we plan to double the company size within 2 years. And thank you.
Yes, Anouk, thank you very much. Very nice presentation. And we will continue then with Frédérick Bordry. Frédérick Bordry, representative of Gauss Fusion. Welcome, Frédérick.
Thank you, Dario, for the introduction. Okay, I will share my slide and to introduce you. I have to find it. Can you see the slide?
It's loading. Yes,
Okay.
We
Yeah,
see
okay.
the full present. Yeah. Can you go to full screen, please?
It isn't full screen, not now. It should be okay. Okay. Good morning. Pleasure to be with. Can you see?
Yes.
Okay, then I will introduce you Gauss Fusion, with the goal is to accelerate the establishment of fusion energy on the grid in the next 20 years. We are special because we are founded by an industrial company. We are an industrial company founded by this, you can see on the left, this company, successful company, who are already working in different domains and being also a supplier of different projects as ITER. I will nominate AHG, what is the company of superconducting magnet in Italy, the group Alsan Alcimex in France, specialists of tritium, but also in different technology, as we were doing initially the beryllium wall, first wall in ITER. Bruker Group, which is a world leader in the medical MRI and NMR, but also producing of niobium restricted magnet and niobium titanium magnets. IDOM, what it is a large group of system engineering in Spain with more than 4,000 engineers and research instruments, also working deeply in energy physics accelerator and in fusion, working in large system of superconductivity. Then what we want to do is we call our motto fusion with integrity. We want to goal is to in a challenging time in the next 20 years to have a 1 gigawatt electrical accelerator connecting on the grid. For that, we are, I don't see all my slide because you're hidden. Okay, we are industry, we want to pan-European, in Europe, we want to be, we are convinced we can only work at the scale of Europe, and we establish partnership, collaboration agreement with the different renowned institutions as CERN, NEA, IPP in Garching and Greifswald, KIT, DIFER in Eindhoven. We had already in presentation. Technical University also Eindhoven, and so on. You can do Technical University of Munich and so on. Then we are establishing more and more partnerships to get this private-public partnership. Okay, this is more or less what we focus. We just to say that we are on magnetic confinement because we are convinced it is a higher technical maturity. We decided it was the first choice made after deep analysis, and I think we are in line with our dear colleagues from Renaissance Fusion and Proxima that stellarator is a more suitable concept for fusion power plant. We are focusing on the first phase of key technology, magnets, high superconducting magnet, tritium full cycle, and plasma heating. We choose ECRH, and we are discussing, for example, with Thales about Girotron and 170 gigahertz all integration. And as I said, we have a very strong cooperation with leading research institute for the design of all these parts. I think we are considering as unique because we're combining existing successful large industrial group and science. And we are mainly engineering because our goal is really to do that. I will skip this because Anne presents that. We are convinced that stellarator is better tokamak. I will add one thing because tokamak is a pulse machine. Stellarator is a DC machine. As especially the magnet, I know the superconducting pulse magnet is not the best to do that. And also in terms of duty cycle, tokamak, you have to stop time to time the plasma to recharge your central solenoid, and you are losing the duty cycle. Okay, this I will skip. This is to give you a flavor of what could be our stellarator. We decide us not to be high field, but to use HTS for high temperature. We are now designing our stellarator to be at 5 Tesla, and to be on the coil between 12 Tesla, where we can use as a baseline HTS, and we also to have a backup LTS. Okay, you can see this is the size of the accelerator, which is 56 meters of diameter, and you can see this design of our coils, what it is 40 coils, and with 5 families of coils. This we are looking not only the device, but we are looking the global thing, because I think we have to design a fusion power plant, and we have now already a design of what would be our fusion power plant with a classical part, which we have a substation to feed all the facility, cryogenics, accelerator, and so on, and also to later when we're producing energy to connect to the grid. And all this water cooling turbine with turbine, and also this is part of about accelerator with all the building with a tritium plant and cryo plant and all cell. I think this was very important. We are looking now more and more the completely fuel of cycle and to take into account the things. So we are also discussing from beginning a nuclear safety requirement and a nuclear safety objective. And we are also now looking in detail different site location, potential site location in Europe. Okay, this is our roadmap. As I said, in 20 years, then now we are in the first phase, 23-25. It is what phase of conception. Then we want to produce a full detailed conception design report. We have already a pre-CDR written, but we want to define what it is, what we want to do, and to demonstrate we have no more showstopper. I think our main thing is mainly on the tritium fuel cycle to produce in a closed loop the tritium. After that, we will have a phase of system engineering, where it is 7 years to really do hardware to, for example, to produce a full coil at 12 Tesla and to cool down, to power, to quench, and to test. We want to do a loop of tritium. We want to set a complete system with Girotron, power supply, transmission line, and so on. To test all the key elements with hardware to be prepared to start construction in, let me say, 2033, and to have this after that assembly and construction of the 6 gigawatt electrical power plant with a stage approach with commissioning to start with, first of all, DD, deuterium, to have the DT in open loop and to close the loop with the TBM, tritium breeding module at the end, and to be ready 2045 to connect to the grid. I will summarize to finish with that, and so it is our milestone. And we are now working deeply on a demonstration of the conception of our 3D magnet, and also especially what we develop is the demountable coils to be able to have easier manufacturing of the coil assembly, and also to access for maintenance to the vacuum vessel and to the TBM and to the first wall. We are doing now a design of this TBM in terms of modular approach. And we foresee now to have, we are designing that a coil tester, a full one coil to test the 3D model, and to assembly also a first vacuum vessel, and to begin the construction, as I said, in 2033. And this is more the roadmap after that than to start the construction and to foresee to have just before 2040 the first Giga, which Giga is our Gauss Fusion 1 gigawatt electrical power reactor, and to have the first plasma just before 2040, and to, as I said, to have this test approach to be connecting to the grid in 2024. Then let me to thank you for your interest, and also we are hiring, and you have this QR code you can get, and also you can look at on the our site, the post open, or you can declare yourself if you have dynamism and wish to work in fusion. Thank you very much.
Thank you very much, Frédérick. Then we will have the final presentation from Jorrit Lion from Proxima Fusion. Jorrit, welcome.
Thank you, Dario. Yeah, great to be here. Exciting times still, and it's getting even more exciting. It's great seeing like 100 participants in this group. Yeah, my name is Jorrit. I'm co-founder, or one of the 5 co-founders of Proxima Fusion, and I am chief scientist in the company. I'm just sharing screen here very quickly.
Yes.
That works.
Yeah.
Great. Yeah, so my idea is just to give you a brief overview about what Proxima Fusion is, and maybe what's also like the distinguishing points are, maybe to the other companies that we have. I'll try doing this. So what is Proxima Fusion? Proxima Fusion is, as far as I'm concerned, the youngest fusion company in at least Europe. It's founded in January 2023. It's a spin out from the Max Planck Institute for Plasma Physics. So lots of the early team from the company have worked and did research in the Max Planck Institute for Plasma Physics, basically where Wendelstein 7X was built and is operated. Our approach are QI stellarators for steady-state fusion power plants. QI is for quasi-isodynamic. This is like this type of symmetry that Wendelstein 7X uses. It's a particular type of stellarators that has the advantages that you want to have from stellarators, which is the low toroidal, net toroidal current that you have and that you want to eliminate in stellarators. So this is QI was like always the path for Proxima Fusion. It's a Munich-based startup, so we're in central Munich, not in Garching. Actually, this week we've moved now from Ostbahnhof. Now we're in Sendling, but it's still Munich. We are a VC capital funded company. We raised about 30 million euros over the time that we've been operating, and there's also public funding that went into the company. So we have secured public funding of another 30 million euros. So there was a team growth in Proxima Fusion from about 8 people in 2023 to about 45 now. And with this, it's a fast growing team. It's a very exciting, dynamic environment. So what's the technical vision? So we plan to build on top of Wendelstein 7X. We think that fusion is hard enough. We want to place deliberate risks where and only where it's necessary. We know from Wendelstein 7X that we can do certain things better already by now, and these are the things that we are planning to address. So there are a few things that are resilient when we think about Wendelstein 7X and look forward onto a next step machine, and these are, we need to change the configuration, so we need to change the way how we assemble the coils in a way that the physics performance that we need for a reactor is cured. That's one, and the other one is like we need to have much higher magnetic field strength. This is very clear from Wendelstein 7X. If we don't want to build these 20-meter major radius machines, we have to trade off machine size for magnetic field strength. So the high field path is the one that we are pursuing. We're also building on top of Wendelstein 7X, and one aspect here that we always see in Wendelstein 7X are these non-planar magnetic modular coils. It's something that Wendelstein 7X has pioneered, but there are also other things that Wendelstein 7X has de-risked, which is, if you think about the diverter concept, that's one. Steady state operation is one. The way how Wendelstein 7X operates with the ECRH system, for example. So there's much to learn, and there's many things that have been de-risked in this machine, which is worth keeping for the power plant vision. Everything that you move away from, or every technology that you move away from the existing technology is always an TRL list, risk technological readiness level list. So we're looking at high field plasmas, 8 Tesla or more, and these are QI devices that we're looking at. You see a part of the team now. This is a photo from summer actually. So lots of people from different environments, like usually like we have an international team, people moving from all over the world to Munich to work with us. There are academic backgrounds, but also like startups, people from other startups. That is maybe something that will come back later in the discussion. If you want to work in a startup, it's of advantage to have like experienced the environment of a startup. It's different than in a bigger company. We also have advisors from Wendelstein 7X. So there are particularly 2 advisors worth highlighting. One is Lutz Wegner, who's head of assembly or was head of assembly of Wendelstein 7X. He basically built Wendelstein 7X. And then we have Felix Schauer, who's not shown here in this diagram, and this photo was the chief engineer of Wendelstein 7X. So these two people are helping us to port the knowledge that we have from Wendelstein 7X to our new devices. Our approach, maybe if you want to boil it down, is maybe to 4 things or 4 distinct themes. One is that this QI symmetry that we're pursuing. So stellarators that have this particularly symmetry in the magnetic field, which is important. We also pursue simulation-driven design. Stellarators are, we typically say, hard to design, easy to operate. The approach from Proxima Fusion is to abstract the difficulties of the design of the stellarator away. There are lots of the team that has been working on stellarators, me included. I've published myself on stellarator power plant studies and stellarator optimization. But now we have the tooling that just where we can really abstract the difficulties of stellarators design to simulation and to simulation-driven tooling. Then we think that also speed is very important. So we have adapted this philosophy of speed in a startup. Speed is the ultimate asset in a startup. We are backed by former successful tech founders of other successful startups, which bring this expertise of how to run such a company into Proxima. And we think that Fusion needs to be treated right now in this situation with ambition and scale, in the sense that we really need to go fast and move on aggressive timelines. And we're also collaborative, so we believe in the speed by exchanging knowledge and ideas, especially with public partners. We are interested in goal-oriented research that's different to curiosity-driven research. We believe that research, it's worth funding research that just that looks into concrete outcomes. Oftentimes with fusion research, there's a little bit of the ambiguity in which of the 2 categories it falls. But yeah, we are working with IPP in Greifswald and in Garching, KIT, PSI, and others. That's our power plant vision. We call this Stellaris. It's a DT machine using HDS superconductors, high field. You see a visualization here on the right. It's currently it's prepared for publication. So our approach is to have that approach peer reviewed by the community. You see a size comparison here of one of the biggest components, the TF coil of the Stellaris device, compared to other devices that have been suggested. ARC, for example, it's the concept from CFS, Commodore Fusion System in the US, and ITER. That's a visualization of this, so an artistic rendering of it. What we are doing different maybe than other startups or companies, we are going via an intermediate step device. We call this machine Alpha. We move away, or we move on top from Wendelstein 7X over this Alpha machine towards Stellaris. And while Alpha is going to higher power and higher field, after Alpha, the economics aspect has to be addressed towards Stellaris, which is after this. So Alpha is dated to about 2031. There's also a hardware R&D program. So this is a fundamental aspect of Proxima Fusion. So we are developing HDS magnets also together with public institutes here, for example, the Paul Scherrer Institute in Switzerland. And we also now have an in-house lab that we are doing hardware prototyping in. Public-private partnerships are a big aspect of our program. In case you're interested, we are interested in collaborating on a project-based scheme. So if you do research or will do research on a related aspect that falls into our technical roadmap, please let us know. We can support in some ways. All right. Just 3 points maybe as a quick summary. So Proxima Fusion is a European stellarator startup. We are in Munich. we have this next step accelerator. It's about Q greater than 1 or Q greater than 1 capable, and we are hiring. It's linked here under our website, and this changes over time. It's worth checking in every now and then in case you're interested. All right.
Well, thank you very much,
Thanks
Jorrit.
very much.
And thank you very much to all the speakers for their presentations. We wanted to make the presentation short just to get all of you an overview of what the companies are working on, and we hope that you will go and contact them directly and see what they're working on more detail. So the chat is now open for questions, but we will start our discussion with the panel members, perhaps seeing their point of view from the area of education and training. So I would like to ask the panel, and please feel free to answer whoever wants, or as many as you want. What do you think are key areas in education and training that have to be particularly addressed to increase the fusion workforce? So who wants to take that first? Annie, I see you on mute.
Yeah, I can start. Well, first, I think that education, I guess, starts even before university, and we think that science popularization, general public awareness about fusion is important to then be able to foster an increase of the workforce. And yeah, we also believe that actually private-public partnerships programs to give students the opportunity to be more familiar with industrial experiments and challenges would be a good idea.
Nice.
I can complement. Definitely, we will need a lot of fusion. We'll need in the future a lot of physicists, but many engineers. I think now is time of engineer. We had a lot of investment in research. It was mentioned that the research was very important, and all the progress done up to now, and thanks to all these previous things. But now is a time for more engineers and so on. Then we will need engineers, and we are looking this difficulty to have engineers in all the domain, magnets, in terms of materials, in terms of tritium, in terms of nuclear things. We will need all this domain. We have to build this ecosystem. I think this ecosystem was pushed in Europe thanks to the JET initially and to the ITER program. But now we have to continue, and I think I'm very pleased to see all this initiative and all this company, because we have to base on this ecosystem and not to miss. Now ITER is finishing installation and so on. In Europe, we need to do that, and we have to target this development and education around all these different specialty. We need to build a full fusion power plant, not only a accelerator or tokamak, but a full fusion power plant. And we will need, we share that with other domain. We need in power conversion, in cryogenics, in the cooling, ventilation, and so on. This we will need a lot of engineering technicians in the future.
Yeah, I agree with that. Yeah, Jorrit, go ahead.
Yeah, I also second that point. Just to complement it, so I also think that we need to have a lot more engineering and engineering expertise in the special fusion field with the special technology that is basically on the edge of everything that we do in terms of like high magnetization, vacuum, cryogenics, high heat fluxes, neutron particle bombardments, and these things. So it's a very exotic environment. But there's also the physics aspect that will always play a role also when it comes to like designing machines and diagnostics and running and operating machines.
Yeah, let me perhaps model the question a little bit more, and then I'll go again. So because there have been some questions in the chat, and also related, like what kind of prior experience what the people need to work in your company. So let me rephrase and summarize that question in the sense of what type of candidate profiles you consider will be required in the ongoing and future projects developed in your companies. Are there any particular distinction between scientific or technological background profiles that perhaps include soft skills and other kind of non-formal training besides the technical one? So perhaps I can start with Dan, and then we can move on this.
Yeah. So we are, let's say, slightly more narrow or focused than the other panel members here. But for us, really, the the key thing is that there are software skills basically, and these are typically in engineering degrees kind of under represented. Often, if people have really strong computing skills, they obtain these themselves. So it's also a bit of an answer on the previous question, of course. So that is really important. And since these codes there's a lot of international collaboration using open source codes, using commercial software, using many different tools. You need to be really, really good at reaching out. Kind of these are the soft skills that are important to make this work. I think it's a combination. You can be very effective just kind of diving down, but I think at a larger scale to be effective, it's really important to be able to build a network of compute tools and connections that you can use.
Nice, thanks. And then from you, the others.
Well, I can try to answer to your question, Dario. I think we need people with passion, with motivation, with the soft skill is the more important. I think we are in the dynamic domain. We need these kind of things. After that, definitely, I think it's our vision. Now it's time to build the things. It's time to build prototype. It's time to build model, to go towards these things. Then we will need a lot of engineer, technicians, and so on. It's time to that. Research, I agree with Jorrit, is very important, and we need that. But we have still a lot of research institutes and so on. We have to continue to work with them. We need few, I think, we are position in our position, but we need people wanting to build something and to be pragmatic. I have could see in the chat other things. We are hiring in different domains. Young people just after a master, after engineer diploma, about PhD. We want to have a team. Homogeneous team with people with experience, having already industrial experience, but we need also young people with a dynamism to do that, but ready to build something. I think for me, it's time in Europe to build a fusion power plant.
Nice.
Maybe to add one point on this, I think there are two types of profiles that we're looking for. One is like really senior people that have lots of experience and then just can own big chunks of the work, which is one. But then there's also the other, let's say, group of people that are just like really people that get stuff done and have shown this and are really driven and motivated and drive success proactively. And as Frédérick said, in a startup, it's dynamic, so the role will change. If you start with something, half a year later, it's probably something completely different. The most resilient thing is to have a solid background, foundations, that is software, but also professional skills, and just really the aptitude to just get things done.
That sounds like a nice comprehensive summary of the profile of the candidates. I will proceed with maybe one last question, but please to the speakers, there are some questions in the chat that are addressed to some of you directly. So please, if you can find the time, maybe even after the presentation, to answer to them, that would be great. There is also a question about, and you briefly mentioned opportunities for students. So perhaps concrete ones. People want to know if you have internships for master students. How can they, is the best way to reach you for an interested student to be working or collaborating with you? So what would you say?
For me, clear, yes, and please look at our site and send us your CV and your proposal. Very clear.
Yeah, I would say the same. So we had lots of interns who had a significant impact on the company, and just look at the website. If you see some offers, don't hesitate to apply. And also, if you are motivated, don't hesitate to contact either the HR or people on LinkedIn, or if you find some contacts, do not hesitate.
Wonderful.
Yeah, just reaching out on LinkedIn also to me directly. That works for us.
Yeah, same. Just send an email. It's internship catalogs are typically kind of behind by a few weeks or months. So just communicating directly is fast.
Okay, wonderful. I think I certainly encourage all the attendees that are interested in working with the private sector, please to address the companies here present. And of course, for the speakers, if you want to share some material with the attendees later on, please send it to us, and we will have later an email sent to all of the participants with the feedback forms and your information. I think we have reached the end of the session. There are many things that we could discuss, but I think this is just an overview. We wanted also the students to know who are the people behind the companies, what are your goals, what are your ideas, and how are you now integrated into the fusion ecosystem in a strong position, and how this collaboration between private and public sector will lead the fusion effort in the upcoming years. So I would really like to thank you for being here. Certainly, we support your initiatives. I think most of the companies present here are Fusion members. We'll have maybe a discussion with Jorrit later on about Proxima. But anyway, all of you support education in Fusion. That's why you're here, and appreciate that. And yeah, we're looking forward to having the future workforce involved in your companies as well.
Thank you.
Thanks.
Thank you very
Thanks
much
for
for being
Thank you,
organizing.
Dario.
All
Thank
the
you.
best.
Yes, thank you.